In this video, we're going to start Chapter 7 of the Calculus textbook. Chapter 7 is on techniques of integration. And so in Chapter 7, what we're going to do is we're going to go in depth into all of the different techniques that we can use to solve integrals. And what does that mean, solve integrals? Well, for the indefinite or definite integral, that just means find the antiderivative. So really, Chapter 7, what it's about is techniques for finding antiderivatives. And we actually started this process previously in sections 5.4 and 5.5. In section 5.4, we were introduced to the term indefinite integral. And then from there, we learned how to solve what I called basic integrals. And what a basic integral is, you're finding an antiderivative of a basic form of a function, of any one of the functions that we're familiar with from algebra or trigonometry. And so to solve these, what we do is we reference a table of integrals like this. And so you can see all the basic forms like the inverse of the power rules, the power rule for integration, the integral of 1 over x, e to the x, the trig functions, exponentials, inverse trig functions, etc. And also actually included in this table were two basic properties of integrals. So the fact that if you have a constant multiple, the integral of a constant multiple times a function, then you can bring the constant multiple outside of the integral. Or the sum and difference rule, to where if you have an integral of a sum or difference of two functions, then you can separate that into two separate integrals. So a basic integral was an integral that you could solve by just referencing this table. Okay, but then obviously functions can be more complicated than just a basic form of an equation that we're familiar with. You could be multiplying two different types of functions, dividing two different types of functions. You could have compositions of functions, etc. And so in section 5.5, we learned the substitution rule, which allowed us to solve certain integrals that were a little more complex than just basic integrals. And then from there, we took a detour and went into some applications of integration in Chapter 6. And now in Chapter 7, we're coming back. We're kind of coming back to where we left off after section 5.5, and we're going to go through all of the different techniques that you can use to solve integrals, at least all the techniques that you learn in Calculus 2, okay? And so in this video, we're going to go through section 7.1. We're going to learn the technique of integration by parts. Okay, so this chapter opens by, it gives that table of integrals again. And it says, because of the fundamental theorem of calculus, we can integrate a function if we know an antiderivative, that is, an indefinite integral. We summarize here the most important integrals that we have learned so far. Yeah, so to solve any integral, a definite or indefinite integral, it's all about finding the antiderivative of the function in the integral. So it makes sense that a major part of Calculus 2 is learning all kinds of methods to find antiderivatives of all kinds of different types of functions, of basic functions and complex functions. But we typically don't say that we're finding an antiderivative. We just say we're learning how to solve integrals, techniques for solving integrals, or techniques for performing integration. In this chapter, we develop techniques for using these basic integration formulas to obtain indefinite integrals of more complicated functions. We learn the most important method of integration, the substitution rule, in section 5.5. The other general technique, integration by parts, is presented here in this section. Then we learn methods that are special to particular classes of functions, such as trigonometric functions and rational functions. Integration is not as straightforward as differentiation. There are no rules that absolutely guarantee obtaining an indefinite integral of a function. Therefore, and again, they keep saying indefinite integral because we're learning that's the indefinite integral is technically the antiderivative, right? But again, even with definite integrals, it's all about finding the antiderivative. So therefore, we discuss a strategy for integration in section 7.5. Yeah, so integration is more difficult than differentiation. It's not as straightforward. Like they say, there's no rules that absolutely guarantee obtaining an indefinite integral or an antiderivative, but it's not so bad. You'll get used to it. Just takes a little more practice. And so what they're going to do is, because it's a little more complicated, in section 7.5, they're going to lay out like a general strategy and approach you can use given any integral. And at the end of that section, they give there's 80 integral practice problems, and I'm going to do like a marathon video where we work all 80 of those problems. So, because that's really the key. It's repetition, practice. And so, but as it says, the most important method of integration, it says, is the substitution rule. And then there's the other general technique. So yeah, like if you have like a basic form of a function and you can just reference like a table or just your knowledge of differentiation, just by intuition, get what the antiderivative is, what the integral is, then that's the first option you'll go to. But outside of that, right, in terms of like actually having to use a certain technique to get the integral, there's two general techniques. One is the substitution method, and the other is integration by parts. The other methods that we're going to learn in this chapter are more associated with particular classes of functions, like trig functions, etc. The substitution method and integration by parts are general. They apply for any, it doesn't matter what types of functions you have, or how they're composed, or how they're put together. Okay, so integration by parts. Every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule for differentiation. Okay, yeah, so if you come here, this is the power rule for integration. This obviously corresponds to the power rule for differentiation. Okay, so the substitution rule corresponds to the chain rule for differentiation. Integration by parts corresponds to the product rule for differentiation. And I didn't go into too much depth on for the substitution rule video when we went through that section. I didn't go through the proof of the substitution rule in detail. I mean, it's they're kind of just stating the obvious, but you can go check that out if you want. But so just to see what they're talking about, how this is the integration by parts comes from the product rule. So, okay, you've got f of x times g of x. You take that derivative, and as we know, the product rule, that's equal to f of x, g prime of x, plus g of x, f prime of x. The derivative of the first times the second, plus the derivative of the second times the first. This is kind of in a different order, but that's the product rule. And so what they do then is they integrate both sides of this equation. And so when you integrate this, that becomes just f of x, g of x, right? Based on the fundamental theorem. The integral of the derivative of something is just equal to, so that this integral is the antiderivative of this, right? Well, what's the antiderivative of this? Just f of x times g of x. And then you've got the integral of this side that they just write into the integral. They haven't done anything with this, but put it into an integral. Okay, then they separate this into two separate integrals, and then they just subtract this integral from both sides, and that's it. That's integration by parts. That's how you get the formula for integration by parts. And so you might be thinking, well, what is this? How does this help? We'll get to that, but this is integration by parts. The idea is you're gonna start with an integral that you're trying to solve, and you're going to choose what you're gonna treat to be like the f of x and what you're gonna treat to be like the g prime of x. And then when you make that choice, then you can come here and you write out, okay, f of x times g of x minus, and then the idea is you're left with this integral that you need to solve. And what happens is if integration by parts works, this becomes a simpler integral than what you originally had. So it's a simpler integral that you can solve with basic integration techniques or substitution or whatever, or any other method that we're going to learn in the upcoming sections. That's the idea. So that's integration by parts, and you're going to remember it more from this perspective. So if you let u is equal to f of x and v equal g of x, so here's f of x, here's g of x. Well, this is g prime of x, but if you just let u equal to f of x and v is equal to g of x, then the differentials So we're working with differentials like we did with the substitution method. We're going to be, these du's and these dv's, dx's, etc. We're going to treat as differentials. Even if they're inside the integral, we can treat them like they're differentials. Go back to the substitution method video if you find that confusing, what I just said confusing. But so we can operate with these du's and dv's and dx's like they're numbers. That's what a differential is, a number, right? So du is f prime of x dx. Again, if what I just said confused you, make sure you go back to it's the substitution method video where we go through the textbook section for the substitution method. I explain this in detail. All right, so the differential then, if u is equal to f of x and v is equal to g of x, then the differential du is equal to f prime of x dx, and dv is equal to g prime of x dx. So by the substitution rule, the formula for integration by parts becomes, by the substitution rule, so what are they saying here? Yeah, I think what they're saying is just we can substitute, so like g prime of x dx, right? There's g prime of x dx. We can just write dv there. And the substitution rule explain why we can treat dv like it's a number. We can operate with dv and du like they're numbers here. We're treating them like they're differentials. Because otherwise it wouldn't make sense to, we never said, whenever we defined the derivative and we had this Leibniz notation, dy dx of a function is equal to, 2x. We never said anything about that you could multiply both sides by dx and solve for dy. Dy dx was strictly a notation for like an operator for derivative. This was the equivalent to saying using the differentiation operator. There was no allowance for looking at this like it was an actual ratio. But again, when we developed the substitution method of integration, it kind of became a little more flexible with this. They're saying that in integrals, it's permissible to operate to treat the dx in an integral like it's an actual number. And to do that, you treat them like they're differentials. So go watch the substitution method video if you need. So okay, so this is dv, okay, and then f of x is just what? Is just u. Right? U is f of x, and then g prime x dx is dv. So you got the integral of u dv is equal to uv minus the integral of v, and there's du. And this is the integration by parts formula that you're going to end up memorizing. The integral of u dv is equal to uv minus the integral of v du. That becomes like second nature to you. Okay, so if we look at an example here, what's nice about integration by parts and even the substitution method, but really more so integration by parts, is that it's general. So you can do this, set up an integration by parts formula for any integral. It doesn't matter. Like kind of with the substitution method, sometimes you could always make a substitution, but it doesn't always work in the sense that it doesn't always like remove all of the initial variable, right? That's the idea. You make a substitution and then with the differential and the main substitution, the entire original variable gets removed, and you're left with this simpler formula. So it doesn't, work every time. But with integration by parts, you can always make this formula. You can make this formula every time. Just what's going to happen is though, to see whether it quote unquote worked or not, you're going to look at this integral here, and it needs to be, you have to be able to solve that integral. That's the idea. It's going to be simpler than what you originally had. And so, one reason I'm saying that is because when you're doing integration by parts, you're going to choose, you have two separate functions, right? A u and a v. You're going to choose one part of the integral to be the u and the other part to be the v. If it doesn't work, then you can just go back and try it the other way. Okay, so for me, the way I look at it, and this typically works, is that we see that, okay, one function is the x, the other function is the sine of x. Look at both of those and say which one of those is easier to integrate. Which one of those is a cleaner integral? The cleaner integral you're going to label as is going to be the v. So if we come here, you go to the original integral, one of those is going to be u, and the other one's going to be dv. because that's the form that you're starting in. So if I look here, okay, so to me, let's make x the u. What we do, u is equal to x. So we'd say u is equal to x, and then dv is equal to sine of x. Because why? Because, all right, so the next step is what you do is you get the, okay, here we're missing the differential. So du is equal to what? Dx. That's really clean, right? Now here we're missing the actual function, so we say v is equal to, and now we got to take this integral. It's minus cosine x. And you don't need to put plus c. We'll get the plus c will come in the end. For the process of integration by parts, you don't have to put plus c here for this integral. All right, so now from there, so this integral here is, we'll write it out here, this integral x sine of x dx is equal to uv, so minus x cosine x, then minus the integral of v du minus cosine x dx. And there you go. You see, I mean, let's simplify this. So we bring the minus sign out, plus, right? You see v, what is v? Minus cosine x. What is du? It's dx. What is u times v? U times v. What is u times dv? That's the original function. And so, so now look, we can evaluate this. We know the integral of cosine x, that's sine x. So, okay, and so we didn't include a plus c here because it was unnecessary. The reason is because, okay, if you don't include the plus c here and you go through the process, you get to this point, this is your capital F of x, right? If you take this derivative, you're going to get x sine of x. So we know that. So that's capital F of x. This is like all this has x terms in it. So now to get the general derivative, we just do plus c. Minus x cosine x plus sine of x plus c. Right? The first step is to get the expression, the entire expression, every single term has the variable in it. That's like the capital F of x. That's the function where when you take its derivative, you get the original function. And then all you do from there is to make it as general as, to make it completely general, you add to the back end of this, you add plus c. Okay, our aim in using integration by parts is to obtain a simpler integral than the one we started with. Thus, in example 1, we started with the original function and expressed it in terms of simpler integral. Yeah, so the idea, what they're saying is that the purpose of integration by parts is, so we chose what was the u and what was the dv. And then we plugged that into the formula and we got this. The whole idea is you compare this integral to the original one. If this one's simpler, then you've succeeded. You chose the integration by parts worked. You chose the right substitution for u and dv. It's not like integration by parts will work every time no matter what. There might be a case that no matter which you choose for u or dv, then you can't get a simpler integral. But that's how you will evaluate if it worked, though. If integration by parts worked, you'll compare this integral to the original integral. And so they just give an example. What if we would have chose sine of x as u and x as dv? To me, it doesn't seem like it'd be that bad because, an integral of x to the first isn't so bad. 1/2 x squared, right? And then the derivative of sine of x is just cosine of x. But they plug it in, and here's the integral. And that's more complicated, right? This is correct. This is absolutely true. This equality is true, but it's not helping us what we're trying to do. We're trying to solve the integral, and this is more complicated. It is in this case, but you might look at this, and for some reason you get lucky, and it seems more complicated visually, but then you look and say, well, look, I can do a u substitution here. I couldn't do a u substitution originally, but if I do a u substitution, then it actually works out. Well, then great. You can go ahead. Or if you get to this point and this integral looks more complicated than the original integral, but you can think about one of the methods that we're going to learn in this chapter. You look at this and say, well, I know how I can solve this. I couldn't solve this, but I can solve this. Well, then go ahead. But again, the general rule, though, to follow is one you're going to choose as what you're going to need to integrate. The part you're going to need to integrate. The other is going to be the part you're going to need to differentiate. And the rule of thumb is to start just whatever is the cleaner, simpler process. And for both of those regards, that's what you're going to pick as your variables. Okay, so it says evaluate the integral of the natural log of x dx. So the two functions here are 1 and natural log of x. This is 1 times natural log of x. So yeah, so why would you, what jumps out at me here is the natural log of x, the derivative of natural log of x is easy, 1 over x. And then they're saying we don't have much of a choice because, well, how could we choose for dv to be the natural log of x? Because we don't even know, that's what we're trying to solve for. So we have no choice. We have to choose u is equal to the natural log of x. But even for another problem, if I see the natural log of x, I think that's an easy derivative. Du is equal to 1 over x dx. It's an easy derivative and it gets rid of the natural log. So yeah. Now, dv is equal to 1. So v is equal to x. Okay, no, so there, I'm getting this wrong here. So, okay, the way you do it, so let's come back here. For the integral of x sine of x dx, the way you do it is, so they chose u is equal to x, so you take the derivative and you get the differential du is equal to dx. And then you say, so integration by parts is u dv is equal to uv minus the integral of v du. So then they said dv is equal to sine x dx. Okay, so yeah, I'm messing that up. It's u is equal to the natural log of x, and then dv is just equal to dx. So if we come back here, I should have said, so u is equal to x, and then dv is equal to sine of x dx, right? So you got to, I should have chosen a u and a dv, so it takes up the whole integral. Du is equal to dx, v is equal to, so if you integrate both sides here, you get v is equal to, because we differentiated both sides here, integrate both sides here, v is equal to, and you just take this antiderivative, but you don't include the constant. That's the idea. Okay, so u is equal to natural log of x, differentiate both sides, and then you multiply by both sides by dx to get the differential. Du is equal to 1 over x dx. dv is equal to dx, integrate both sides, v is equal to x. So what we've got is the integral of the natural log of x dx is equal to uv x natural log of x minus the integral of v du. V du, x times 1 over x is just 1, so just dx. That's definitely a simpler integral. So this is x natural log of x minus x. There's your capital F of x, so now just add the c. Okay, let's do this one here. T squared e to the t. Well, e to the t has a easy derivative and integral. So would we rather differentiate or integrate t squared? Well, we'd rather differentiate it. So we'll say u is equal to t squared. So du is equal to 2t dt. All right. And then the rest of the integral, the dv is equal to e to the t dt. So v is equal to e to the t. All right, so the integral t squared e to the t dt is equal to uv minus the integral of v du, 2t e to the t. Okay. Have we made this simpler? Well, this is not that simple, but yeah, we have. It's simpler than this. And so they use integration by parts a second time here. And you'll do the same thing. You'll say that you can bring the 2 out, but you'll make like the t will be the u, et would be the dv, et dt would be the dv. And so here's the integral of t using integration by parts. Here's the integral of t e to the t. And then they just plug this in here. But the constant, you can see, ends up, I don't know why they carry the constant. So, okay, here's the original formula. And we just evaluated this integral, this t e to the t dt. And so now we're done. So we plug that in here. Okay. Now, if you multiply the 2, you get that they're saying 2 times c is equal to c1, but to me that's unnecessary. I mean, this is your constant. Like, you don't need to. The c1 is just specifying that this constant. But what's the difference? This is capital F of t. When you take the derivative of this, you get the original function here, and then just add the plus c to the back end of it. Okay. Here, when we comparing e to the x and sine of the x, they're both simple to work with in differentiation or integration. So I guess sine of x, the derivative of sine of x doesn't have a negative sign. Like the integral of sine of x would be minus cosine of x. So let's just say that u is equal to sine of x and dv is equal to e to the x dx. So du is equal to cosine x dx, and v is equal to e to the x. Is that what they chose? No, they chose it the other way around, but I don't think it would have mattered either way. We'd get uv e to the x sine of x minus the integral of v du. Yeah, it should. Well, let's just go with there. They did the opposite substitution. It shouldn't matter either way. And so, okay, they did it with, they said u is equal to e to the x and dv was sine of x dx. Okay, so they apply the integration by parts and they get this. All right. Now, so pay attention here. This is something that you might get tested on. It's important to remember that this is a possibility. And so, okay, so we have this integral e to the x cosine of x, but that's no more simple than the original integral. And so what they do is they just keep going. They do this. They do the integration by parts again here, and they get this. Yeah, it would have worked out either way. They get this here. Okay. So we look here. This integral is still no simpler than the original integral. However, if you notice, this is the same as this. We can add this integral to both sides and get 2 times this integral, right? You get this. Now just divide both sides by 2 and you've solved for the original integral, okay? So just keep that in mind, how this is a potential way a problem can be solved with integration by parts, where you actually solve for the unknown integral itself in the end. Okay, and now the last thing they talk about is integration by parts with a definite integral. And so I'm not going to get into the proof or anything, but all it boils down to is you do the exact same thing as everything what we just did, but this f of x times g of x, you're gonna evaluate that from a to b, and then the new integral is just going from a to b. Okay, so we're going to work example problems, and you'll get the hang of this as well.